So for electrostatics, right, the first thing we need to know is that we're dealing with charges. And if you're dealing with charges, then you know that there must be this invincible force, which is called an electrostatic force. Electrostatic force, which is a force that exists between charges, right? So for example, in this question we have two identical small metal coated spheres, R and S. When they say they are identical means that they have the same charge, isn't it? Yeah, that should mean that they have the same charge. And then they are given identical charge of 40 nanocoulombs each. So this one here is 40 nanocoulombs, and then this one here is also 40 nanocoulombs. They are suspended at the same point. The fact that they are suspended, this should tell us that the F net is 0, right? Because remember, if things are suspended, they're in equilibrium, that means the F net is 0, because the acceleration is 0, they're not moving. Right, and then there is a string here by means of an identical light inextensible insulating thread. The moment we have a thread, that means there is tension inside of that thread. So here should have a tensional force, right? So we should be talking about tension here. Also, we should be talking about tension there. And they're of equal length. Okay, that's okay. That means this is equal to that, which means, what does that mean according to maths? If this one and that, I'm not trying to open the wounds for maths, but you must apply maths. You must understand that when you're doing this, you are doing what we call applied maths. So if these two are equal, that means I can get this angle here and then I can get that angle there. Using what? Sum of angles in a triangle, isn't it? So how do we use that one? Remember, we say 60 degrees plus this angle, I can call it x, plus another x is 180 because of those sum of angles in a triangle. So I'll have 2x is equals to 180. Have my 2x is 120, therefore x should be 60 degrees. That means here I should have 60 degrees, and then here I should also have what? 60 degrees. It's very important to know those angles, by the way. So the statement itself is the one that guides you, understand? It gives you all the information you need to answer the question. The threads are of negligible mass, means that they have no mass. When the system is in equilibrium, again F net is 0. The angle between the threads is 60 degrees, which is this one, while the distance between R and S is 5 centimeters. We don't work in centimeters, we work in meters, so immediately you divide by 100. That is going to give you 0.05 meters. Then you're okay. State Coulomb's law of electrostatics. Let's remember our definitions, right? You know, as you are going to write your physical sciences, it's very, very key to remember all the definitions that you learned during or throughout the year. So this is something that we've been repeating in many instances, that we must know our definitions. So for 7.1, you know, Coulomb's law says, what does it say? Anyone?
On another charge is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance
between them.
between them.
Perfect. Yes, that is how we state it, right? That is how we state it. Very nice. That the magnitude of the electrostatic force between 2 point charges is directly proportional to the product of the size or the magnitude of the charges, and inversely proportional to the square of the distance between them. Okay, so that is it, right? It is stating Coulomb's law. Let me just write it here for just in case. Okay, so to avoid writing my bad handwriting, this is the definition. The magnitude of the electrostatic force exerted by one point charge on another is directly proportional to the product of the charges, to the product of the magnitude of the charges. Yeah, they omitted some stuff. And inversely proportional to the square of the distance between them. Alright, now for 7.2. Yes, ma'am?
Can't we also admit some stuff because they do it? We wouldn't be wrong, right?
Well, the problem is that I think this paper is from KZN. Not that I'm saying KZN, they are not doing the right things, but I just would trust a national paper more than a KZN paper, right? Nothing personal. But yeah, those it's important to state it fully. State it fully. Alright, and then our 7.2 says now we need a free body diagram showing all the forces acting on sphere R. So sphere R only. So for sphere R, we can say you show all the forces. That means even though it is a charge, you must make sure even though it's a charge, there is also force of gravity. Then here you're gonna have tension. So you're gonna have the force of gravity and then you're gonna have tension. This is something that most people miss because they feel like since it's charges, you know, why would I include force of gravity? Well, it has a mass. So because for the fact that that charge is going to have a mass, you must have the force of gravity acting on the charge. Then you have tension. Apart from tension, right? Remember that sphere S is also exerting a charge on R, and since they are identical, it means sphere S is repelling R. That is why R is not touching S. So that means here there is a force of sphere S on R. Okay. So just to recap that, when you draw the free body diagram, treat it as if you are still dealing with your Newton's laws. You must have the force of gravity because the sphere has a mass, and then you must have tension because there was a rope, right? Then you should have S on R, which is pushing R from to that side, right? It's pushing R this side, so it's the force of S on R. Perfect. Then that's how you get your 3 marks. Then for 7.3, to get the mass of sphere R, you still treat it as if you are working with Newton's laws. So to get that mass, right, how can we work on it? So let's remember that here I will take the free body diagram, the very same free body diagram, say copy that and then try to paste it somewhere. Oh, okay. In fact, let me maybe do this. So here you're gonna have Tx, and then here you're gonna have Ty, right? You're gonna have Ty. So you can start wherever, horizontally or vertically. So I'm going to start horizontally. Okay, so horizontally F net is equal to 0. Okay, horizontally, and then I'm gonna choose this side as positive. That means Tx minus, we start with MA. F net is equal to MA. Okay, we say F net is equal to MA first, then we say Tx minus F of S on R is equal to 0 because the system is in equilibrium. That means Tx is equal to the force of S on R, and Tx is T cos theta, and then this guy here is F. So the force of S on R, it's going to be what we use. So let me write this here first, or in fact let me write it like this. So we use 9,0 times 10 to the power 9. You multiply by the charge of S. The charge of S is 40 times 10 to the power negative 9, and then same thing here, it's 40 times 10 to the power negative 9 for S and R. Then you divide by the distance between them, which is 0.05 all squared. In that way, you're going to be able to get the tension, which is going to assist you somewhere, trust me. So now this cos theta there, actually the angle there, what is the angle? That is the one that is going to be 60 degrees, because TX, the angle in between there, is 60 degrees. Then now you can find tension. What's going to be your tension? 5,76 times 10 to the power negative 3 newtons. Is it like this?
Yes.
Perfect. So you got the tension now, but the goal was to get the mass. So for us to get the mass, now since this one was the horizontal, right, now we can work with the vertical, because that's where mass is. Where there is Fg, that's where the mass is. And remember,
Can I ask a quick question?
yes,
Then why did you calculate tension in the X, the horizontal side? I wanted to ask that. Why couldn't you just calculate Ty only by itself?
okay, how would you get Ty? The problem there is that I needed the tension first. Let me show you why. Vertically,
Oh, because, okay, yeah, sorry.
no stress. So vertically you will see that since it's also not moving, F net is 0. Then I'm gonna say Ty minus Fg is equal to 0. That means Ty is going to be equal to that Fg. But now remember, Fg is mg, right? I need the mass. I know that here it's 9,8. That means I must get Ty, which will be T sine theta. Right. Now, if I didn't have tension, then I would be stuck. But luckily we found tension. We can put it as 5,76 times 10 to the power negative 3. Then we say sine 60 degrees is equals to m into 9,8. And therefore, what is the mass of that sphere? Five comma 09
Yes.
times 10 to the power
Negative 4.
negative 4 kg. Okay. Yeah, so that's how you get it there. Yeah, so that's how you get the mass. Quite an interesting question. You need to know your forces, okay? You need to know your forces. Then you should be fine there. So let's look at the next question. All right, so here we are. We have a diagram which shows a boy skateboarding on a ramp which is inclined at 20. Then a constant frictional force of 50 newtons acts on the skateboard as it moves from P to Q. So here on P to Q, there was a constant frictional force of 50 newtons. Right. Draw a labeled, consider the boy in the skateboard as a single unit of mass, 60 kg. That's beautiful. Right. Right, because 5.1 says we need to work on P to Q, right? The free body diagram. So what we can say, 5.1, we can say here's the boy. We know that there will be Fg acting on him. We also know that there will be normal force, right? Sorry. But then there should be also frictional force here as he's moving down. I think he's sliding down. Yeah, he's sliding down. So these are the forces there. Then you get your 3 marks, right? Then point P and Q on the ramp are 25 meters apart. The skateboarder passes point P at the speed VI and passes Q at the speed 25. Ignore rotational effect. Hey, if you had to include rotational effects, it means you're talking about physics in first year. So there's a steady work energy theorem in weights. I'm hoping the definitions, like I said, guys, we need to know these definitions. Yeah. So work energy theorem, remember, it says, what does it say? The net work done on an object is equal to the object's change in kinetic energy. Yeah, it should be saying that. So 5.3, it says use the energy principles to calculate the speed VI of the skateboarder at point P. So we need to know VI here. We don't know it. Do we have, or we have velocity at Q? So we have final velocity here as 15 meters per second. 15 meters per second. So you can see that they said use energy principles. They didn't say use the work energy theorem. So because they said use energy principles, the only formula that I like using, right, and I don't take credit for it. I think Mr. Bishop from Crazy Physics, you should check out his YouTube channel. He is a very, 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 very intelligent guy. So when he was having us as teachers on a convention on the physics in Daba, he once mentioned that this formula, you can use it throughout when you're using working with work energy and power. Okay, so indeed it is it works wonders, this formula. You should know that if you have friction, applied force and tension, then you put you can use this formula there. If you don't have friction, applied force or tension, if you don't have them, you still use the same formula, but here you would write 0. Okay, that's how it works. So in this case we do have friction, so I'm simply going to say work done by friction, because it looks at the work done by non-conservative forces, and the non-conservative forces that we have, remember, it's friction, right? Friction, applied force, and then tension. Okay, so when you have those, you know that definitely you can use you can just write work done by that. If I had friction and applied force, I would say work done by friction plus work done by applied force. Okay, so in this case I only have friction. Then I say half a change in kinetic energy is half m into vf squared minus v initial squared, and then here we have mg, we have h final minus h initial as change in potential energy. Now the work done by friction, you usually calls it friction 180, which means for friction we usually use 180 degrees. So we would say fk, change in x, cos theta, then here we say half m vf squared minus v initial squared, mg h final minus h initial. The friction we're given, so we'd say 50, and then change in x, you must know that change in x is going to be the distance, right? Change in x will be the distance traveled from P to Q. It's given as 25, very nice, and then they use 180 degrees. Okay, and you say half, the mass is 60, right? We're looking for the final. Oh, the final is given as 15. The initial is not given. It's the one you're looking for. The mass is what is the mass? 60. Nice. And then 9,8. Final height though. We don't have heights there. Do we have heights? Oh, P and Q on the ramp are 25 meters apart, and okay, so yeah, in this case we would need to use the work energy theorem. It's probably the best. So what you do now, if you want to change this to the work energy theorem, this part, you no longer write it as WNC, but you write it as WNet. Okay, then the change in KE, you leave it like that. Then this one, you just remove it. So this becomes a work energy theorem. Yeah, and since also we're required to state the energy theorem, it kind of gives you an indication that for the next question, you might have to use the work energy theorem. But like I'm telling you, there is some maths you can just perform to get this part, because this is the only hurdle that we had. If you can get this part, you can get VI. Yeah. Okay, so in that way, you would only leave this part for WNet, right? So this part won't change. 60, 15 squared minus VI squared, right? However, for WNet now, you need to find the net force. And for you to find the net force, you must recognize that here there is FG parallel, isn't it? Then you'd say Fnet change in X cos, remember you'd use 0 degrees. You use 0 degrees. Isn't it? And the 0 degrees, please note that the 0 degrees is this angle here, which is the angle between where the object is going and the force. For friction, it's usually 180. For net force, it's usually 0 degrees. In fact, it's always like that. Fnet is 0 degrees. For friction, is usually 180. So change in X, you have it as I think you have it as 25, because 0 should be 1. Then here I think you should have 30 into I think 225, if I'm not mistaken. You can check for me there, minus VI squared. Then now you would need to find the net force first, so it's just a bit long. So you need to find the net force. So how would you get the net force there? Is the person moving at a constant velocity? No. So that tells you that there is some sort of acceleration. Okay.
I use the work done by friction and work done by FG parallel.
By FG parallel. Yeah, that will still going to work. So it means here for WNet, you can write it as work done by friction and then plus work done by FG parallel. Because remember, the work done by normal force is 0 because it's perpendicular to where the object is going, isn't it? Then for FG, you already used FG parallel. When you use FG perpendicular, the work done by FG perpendicular is also 0. Remember, for FG, we usually use its components again. So that means the WNet is only made up of these two forces there. Yes, ma'am.
So for every case, the WNet is always in the y-axis. You add the forces in the y-axis.
It depends on where the object is going. If the object is going up, WNet can be in this axis. You understand me? For example, if I have tension here and then maybe the FG, and then like things like a motor, if I have a motor or a lift, you understand me? There, those things are moving in the horizontal, vertical. So WNet can be in the vertical WNet, because the object will be going there. So in that case, the forces that will be acting horizontally would be doing 0 work. So in this case, you are saying WNet is here because normal force and FG perpendicular are doing 0 work. Right. So I don't want to say it's always horizontal when there's a possibility that they can also be in the vertical direction. All right.
And here,
Yes, sir.
there's a question that I did, ne?
Yes.
It asked, it regarded a lift, ne? There was, I think it was a 75 kg drum-like thing, man, yeah. You know, those things that is used in construction where you add things, ne?
Yeah.
And then it said I should calculate for the gravitational force. Ne? Now, when I was calculating, it was the second time I'm doing this question. Ne? So the first time I did it, I looked for the gravitational force, which is 9.8 most. Ne? And then I found out that I was wrong. I should have used mg, man. Why is it that like that, man?
Oh, can you repeat for just a sec? Yeah.
It was a question, I think I did it in June, ne?
Yeah.
I was in class. The question asked that I should calculate the gravitational force. Right? Now, when I was calculating the gravitational force, I used 9.8 instead of m times mg, right? Instead of weight. You see me, yeah? Then, yeah, then I got a completely different answer, man. Why was it like that, man?
Gravitational force is mg, right?
Okay.
Right. Yes, the gravitational force is your Fg, which is going to be the mass times g, 9.8. Over.
You.
Yes.
Now use the okay, show me nothing, man.
Yeah, so you must make sure you'd always put it that way. And then for this Fg parallel, because remember Fg parallel is it's Fg sine theta, isn't it? Which also can be written as mg sine theta. So here I substituted the mass as 60, g as 9.8, sine the theta. You should remember that it is the angle of inclination, which is this one here, the 20 degrees, okay? And then after that, this work done by Fg parallel again, you must remember that it's let me just write it down here so that we remember it, because there we can get a bit confused. So it's, for this one it's Fk again, change in x cos theta, whereby theta is the angle between where the object is going and where the force is acting. And then this one is Fg parallel, change in x again, cos theta. You understand me? Then this side is equal to change in kinetic energy, which is what we had already calculated that side. So the change in x there, it's going to be 25. The cos, the angle there is going to be what? 0 degrees, because the object is going down and Fg parallel is also acting downwards. And then you can then put this one this side, 30, 15 squared minus vi squared. In that way you'll be able to solve for the initial velocity. Then you would have solved the answer. So just be careful in terms of these angles. I'm just gonna put a star on them. This angle here, and those angles. This one is the angle of inclination, right? The angle of inclination. And then this one here is the angle between, where the object is going and where the force is acting. All right, then you should be good. So yes, indeed.
Sir?
Yes, ma'am.
So you're saying that is 0 degrees because Fg parallel is going in the same direction as what, sir? Please explain that part.
Exactly, ma'am. Exactly. You understand? Because Fg parallel is this side, the object is also going that side. So the angle in between there is going to be 0 degrees. Are we clear? Is that okay?